Another video for our Lambda class. In this video, we're going to talk about roots of unity and the fast Fourier transform. Um, well, the way of dealing with the problem of representing a polynomial as a list of numbers is a very complicated one in the sense that it's conceptually simple to understand, but it's difficult to implement in terms of a software implementation. This is the reason why we need some theory to speed up the process a little bit. This is going to require that we know some things about roots of unity, especially over the real numbers as a subset of the complex numbers. So we're going to be talking maybe the first half of the video about roots of unity, and then we're going to try to explain how the fast Fourier transform comes in to help us in this problem of representing a polynomial as an evaluation list. Okay, so first of all, let's talk about the complex numbers. Okay, from what we have seen before, the complex numbers is simply the ring of polynomials over the real numbers over the polynomial 1 plus x squared. This is a way of looking at the complex numbers in terms of field extensions. This means that C is a field extension of R. We can see this as adding a symbol called I to the real numbers. In this sense, usually what's said is that the symbol I, when you square it, you get -1, which is precisely what happens when you take a look at C in terms of rings of polynomials. Okay, in this version, we know that the polynomial 1 plus x squared equals 0, so this means that x squared is -1. This later representation in terms of an imaginary unit is simply a renaming of the letter x. Okay, so back in business, complex numbers are simply expressions of the form a plus ib, where a and b are real numbers, such that I squared equals -1. Okay, so this is the usual set of complex numbers. Of course, C is a field. Okay, we can add C is a field. Complex numbers may be added and multiplied together with the usual distributive laws, taking into account that every time that you see I squared, you must replace that with -1. But there's also a new operation in C, which is a conjugation. C is equipped with a conjugation. That means that if we have a complex number, we may build a new one out of the old one just by reversing the sign of its imaginary part. It is said that this guy right here is the conjugate of this guy right here. Conjugation has some nice properties. Okay, one of the properties of conjugation is that it's an involution. When we conjugate 2 times, we fall back into the original complex. And well, conjugation is distributed respect to addition, and also conjugation distributes over products. All right, so these are very, very nice properties. And as we will short see, conjugation leads the way to understanding some geometry of the complex numbers. Okay, so we may represent complex numbers in a Cartesian plane. This is, we may have a representation of the complex numbers where this complex number a plus ab, this is a, and this is ib. Okay, so this point in the plane is actually represented by the pair A, B. So in this sense, C can be understood as the real plane. Okay, you may think of this complex as an arrow from the origin. All right, and it turns out that when you multiply together z and z conjugate, what you get is simply a squared plus b squared, which coincides with the length of this arrow. This is what we call the absolute value of z squared. Of course, this result is compatible with the idea that what we have here is simply a side, a leg of a right triangle. This measure is A, this measure is B, and this just says Pythagoras. Okay, so there's a relation between conjugation and measuring complex numbers. All right, since we have a notion of length, gives a notion of length for complex numbers, we may start to think of certain subsets. And the most important one is actually the unit circle. S1 stands for the unit circle, and it consists of all the complex numbers that have measure 1. All right? All the complex numbers that have measure 1. If you want to take a look at it, it's simply a circle of length, of radius 1. So you can place this just right here. And there you have it. If you bear with me with the precision or imprecision, this is simply S1. All the complex numbers that live right there are simply S1. And it turns out that S1 has very nice properties when we equip S1 with the product of complex numbers. S1 together with complex multiplication gives a group. Okay. We will now show that S1 has some very nice properties when we equip it with the multiplication of complex numbers. Okay, so we will prove that S1 is a group when equipped with complex multiplication. Okay, so to prove that something is a group, okay, first of all, we need to show that S1 is non-empty. Okay, 1 is simply this complex number belongs to S1 since its measure is simply 1. Okay, so S1 is a non-empty set. So we may start working on this. Okay. Then we need to show that now that S1 is closed under multiplication. Okay, so we need to show that whenever we take two elements of the unit circle and when you multiply them together, what we get is another element of the unit circle. So let's try this. Let's pick omega 1 and omega 2, both elements of the unit circle. So we know that these guys have measure 1. We need to show that omega 1 times omega 2 also belong to S1. That's what we need to show. And for this, we are going to need certain property of the complex numbers. So let's do this. Let's try to measure their product. And to make things easier for us, let's try to measure and square its length. So by definition, this is simply these two guys together multiplied, then we take the conjugate, and then we multiply with omega 1 times omega 2. This is simply the definition of square of the absolute value, simply the definition. And now we may use that multiplication in C is associative and commutative, since C is a field. So this means that we can rearrange this expression however we like. And this means that we can, first of all, use properties of conjugation here. Then we can get rid of the parentheses and we can make these two complex numbers commute, so we end up getting the conjugate of omega 1 times omega 1, associate these two guys, and then multiply by omega 2 conjugate times omega 2. And this is simply the definition of the length squared of omega 1 times the length of omega 2 also squared. And now what we get is that since omega 1 belongs to S1, this is 1. And since omega 2 belongs to S1, this also is 1. So this product equals 1. What we have just shown is that the square of the length of the multiplication of omega 1 and omega 2 is 1. This says, by taking square roots, that this product has length 1, and this means that this product belongs to S1. Okay, so the unit circle is closed under multiplication. Okay, it's closed under multiplication. Now we need to show something else. So not only it's closed under multiplications, but also we need to show now that S1 is closed under taking inverses. This is if we have a complex number omega belonging to the unit circle, then its multiplicative inverse also belongs to S1. So that's what we need to show. Okay, so let's pick an element of the unit circle. Okay, let's say we can do it graphically. Okay, so we have this pair of axes. Let's draw a little circle. Let's try to see how this works. So we have this guy omega here, W, omega, whatever you like. And we need to show that its inverse, this is what we need to show. So let's take omega. Since omega is not the zero complex number, then omega has an inverse in C. This means this is because C is a field, okay? So there's an inverse for omega. When we multiply these two guys together, we end up having 1. But then again, taking absolute value, then we have this. And for what I have seen before, this is simply the product of the absolute values. And now, since omega belongs to S1, since omega belongs to S1, then this is actually equal to 1. And that observation yields that the measure of the inverse is also 1. This means that the inverse of omega also belongs to S1. So what we have shown is that S1 is a non-empty subset of the complex numbers, which is closed under multiplication and closed under taking inverses. All this means that, well, since complex multiplication is associated, because multiplication in the complex numbers is, then this means that S1 is a group. Uh, when the group operation is simply the multiplication of complex numbers. Okay, so S1 when multiplication is a group, we usually denote this with this pair. Okay, unit circle and this is scalar complex multiplication. All right. So there's something that's it's really interesting for us, that observation when we take a point which is on S1, then first of all, this is valid for all, let's write it like this. For every omega in C, this is valid. Especially when we consider omegas that belong to the unit circle, we get that the conjugate also belongs to the unit circle. And not only that, also, when we multiply these two guys together, what we get is 1, since this is nothing else than the length of omega squared. This means that the inverse of omega is simply the conjugate of omega. And this is a very important thing that we're going to use later on. Okay, so if we have an omega right here, its inverse is nothing else than its conjugate. This is omega conjugate, and at the same time the inverse of omega. So taking inverses can be seen as a geometric operation on the points of the unit circle. All right. It turns out that this set is very important, and we can right now see that these points on the unit circle define triangles. And if they define triangles with the axis, then we can define angles. Turns out that there's a theorem that's called the De Moivre theorem that will relate the process of multiplication and exponentiation of elements of the unit circle with the representation of triangles. First of all, let's go through some notation. For omega being a real number, we will note e to the I theta as the complex number, cosine of theta plus I sine of theta. This is valid for all real theta. Okay? This is the exponential notation. And from what we have seen before, and from Pythagoras, the length of this complex number is simply the square of the cosine plus the square of the sine, and this is simply 1 by Pythagoras. It turns out that there's a representation of the unit circle as the complex numbers of this form. So the unit circle is parameterized by this expression. Okay, and this is very ubiquitous because this notation of using the exponential or the complex exponential will lead to a very important theorem. Okay, theorem of De Moivre. When you take the nth power or the kth power of elements of the unit circle, not only you get also an element of the unit circle by the group property, but you get this one. And this is a very important thing for us. The relation between how we parameterize the unit circle, the role of the powers, it's all bound together by this theorem, the theorem of De Moivre. This will help us in our study of subsets and subgroups of S1. This theorem will come handy when studying subgroups of S1. Okay? We'll see that in terms of the exponential notation, what this says is simply that whenever you want to raise to the power of k this complex number, what you get is simply k times the argument right there. So in a sense, this power gets into the argument of the exponential, and this is crucial for us. Okay, for k and integer. All right, and this will give us the key to study some subgroups of S1. And this is where the roots of unity come, okay? Come in very handy. So let's start with roots of unity. Okay, so G sub n is simply the set of complex numbers such that when you elevate this to the nth power, you get 1. Nth roots of unity. If a set is an element of this group, well, the set, then Z is a root of the polynomial x to the n minus 1. So the roots of unity are the roots of a polynomial, okay? Simply the roots of this polynomial. And over C, there are exactly n of them. P has exactly n different roots in the complex numbers. That's one thing. This means that this has exactly n elements. That's the first thing, okay? The second thing is G is actually a subgroup of S. G sub n is a subgroup of S1. And that's fairly simple as well, right? The neutral element of S1 obviously belongs to G7 since this holds, and then whenever uh, S and T belong to the roots of unity of order n, then S and T to the power of n is simply this using the commutative and associative properties of multiplication, and this is simply 1. So it says that S times T also is a root of unity of order n. And finally, it's Gn is close under taking inverses. Right, because since, well, if G belongs to Gn, then G conjugate also. You take the nth power, this is simply G times G, all factors conjugate, and then use the property of distribution of the conjugacy, and this is simply conjugate of G to the n, and this is the conjugate of 1, which is 1. So whenever you have an element in Gn, its conjugate also belongs to Gn, and this is simply 1, right? So this means that G conjugate is also the square of G. This means that the inverse belongs to Gn. Okay, so Gn is really a subgroup of S1, with the difference that S1 is an infinite group and Gn is a finite subgroup. Okay, so this S1 acts as an ambient group, an infinite ambient group for Gn. Okay, so there are many examples of Gn. Let's try some of them. Examples: G4, fourth roots of unity. Right? So if this belongs to G4, then Z is a root of P of x, x to the fourth minus 1. And this is not really complicated since this can be thought as a difference of squares. The roots of this polynomial are simply 1 and minus 1. And in the meanwhile, we take a look at this, and the roots of this polynomial are I and minus I. So these are all the 4 roots of P in the complex numbers. And when you take a look at it, G4 is actually pretty easy to visualize. Circle now. Okay, so 1 is over here, minus 1 is over here, then we have I, and then we have minus I. So G4 has 4 elements: 1, I, minus 1, and minus I. All right, and let's take a look. Take this one, for example. When you square it, you get -1. So you jump to this one. If you cube it, then you get -I. That means that multiplying one more time against I with this one. And when we multiply one more time, so we get I to the 4th power, we get simply 1. So in essence, G4 is a cyclic group generated by I. Turns out that this element generates the rest of the group. Okay, when in change, if we take 1, then we get a discrete, simply the trivial element. If we take the powers of -1, then we end up jumping between -1 and 1, -1 and 1. So G4 is what's generated by I. If you take the subgroup generated by -1, you end up having these two guys alone. So this marks a difference between two of the roots. This root allows me to recover the whole group, whereas this root does not allow me to recover the whole group. It shows here that the subroot generated by this element of the group is a proper subgroup of G4. So we have a name for this. We will say that I is a primitive root of unity of order 4. Is it the only one? No, it's not the only one. -I is also a primitive root of unity of order 4. Okay, so that's what we have. There's also more. Let's take another example. Let's talk about G6. This is the set of complex numbers such that when you take the 6th power, you get 1. So elements of G6 are roots P of x equals x to the 6th power minus 1. Okay? So there are a number of ways of taking a look at this, and maybe we can reason by similarity. Here we needed G4, and we ended up slicing the unit circle in 4 places. Like we have 4 slices of this pizza. For G6, we have kind of the same feel to it. Let's choose this one right here. Let's draw a circle. Okay. And now what we have is that 1 and minus 1 are obviously roots of the unity. So we have this one and this one. These are roots of order 6. And then what we need to show, is that by slicing in thirds, we get the 6 roots of unity. This one right here, let's call it omega, is such that omega to the 6th power equals 1. This one right here, we're going to call it e to the power of I 2 pi over 6. Okay, what happens when we start multiplying and taking powers of omega? It's not difficult to show that this is omega squared. This guy right here is omega cubed, omega fourth power, omega to the fifth power, and this is simply omega to the sixth power. Omega is a generator of this group. Okay, and it turns out that all these guys can be written as powers of omega and its inverse. Take a look at it. This is simply the conjugate of omega. It means that's the inverse. Also here, this one right here is the conjugate of omega squared. And it turns out that this coincides with minus omega, right? And omega writes pretty much everything here. One observation, when you omega squared, this guy, ends up generating a subgroup of G6. If you take a look at what it generates, you get, well, first of all, omega squared. When you square this one, you get omega to the fourth, this one. And when you cube it, you get omega to the sixth power, which is this one. It ends up with the idea that we get simply this subset. And this is nothing else than G3. This is the group of roots of unity of order 3. So by inspection, G6, G2, and G3, you get this sort of lattice in which this one is generated by omega, this one is generated by omega squared, and this one is generated by omega cubed. So this subset is actually G3. And when you take a look at, for example, this and this, that's, for example, G2. Okay, so the nth group, the nth roots of unity contain subgroups that relate to one another by the relation of divisibility. Okay, this is very rich for us, and the case that we are going to exploit is a very specific one. When n is actually a power of 2, then let's write it like this. When n is a power of 2 and omega generates Gn, let's write it like this, G to K, then omega square generates G to K minus 1. So this is important for us because it's going to allow certain recursion to take place. And what recursion are we talking about? So here comes the handy thing of using roots of unity. And this relates to the problem of transforming a polynomial understood as a list of coefficients into a table of values. This comes into picture when facing the problem of representing a polynomial as a table of values. Because a polynomial is this sort of object of polynomials in one indeterminate, right? So we may think of polynomials as these expressions. P is a polynomial of degree n minus 1. And it's absolutely, it's completely determined by n values. This is because of the fundamental theorem of algebra, right? So in this sense, one first representation of P will be, okay, we're gonna think of P as a list of n numbers. Okay, and if we want to evaluate P, we need an evaluation set. Let's suppose that P belongs to f of x, f being a field with sufficiently many elements. And by this, we mean that the number of elements in f is way greater than the degree of P. Okay? So what this fundamental theorem of algebra says that we may represent P not only as a list of coefficients, but we may represent it by the values it takes in exactly or at least n spots. What are we talking about? Take over the real numbers. This polynomial can be identified with this list of coefficients. And the theorem of the fundamental theorem of algebra says that this P can be represented by its values in 2 points. Here we get the coefficients, and here we take the values P takes over an evaluation set consistent of 1 and 2. This transformation that takes coefficients to values, we may call it phi, is a bijection. This is a bijection. It's a faithful representation of this polynomial as a list of results. And there's a lot of slack and there's a lot of room in choices here. That's right, another example. Say a polynomial of degree 2. 2 minus 3x plus 5x squared. We may represent this polynomial P as the list of its coefficients, or we may represent it by evaluating P at an evaluation set. Let's choose as an evaluation set, let's choose minus 1, 0, and 2. Okay, so we may represent this polynomial simply by saying what it is. 2 minus 3 times minus 1, that's 5, plus 5, that's 10 right here. 0, that we get 2, and then when we use 2, we get 2 minus 6, that's minus 4, plus 20, that's 16. And this is a representation of P in terms of the values it takes when evaluated at this evaluation set. This is P of minus 1, P of 0, and this is P of 2. Right? This transformation that's associated with this evaluation set will allow us to transform faithfully every polynomial of degree at most 2. All right? So this operation of codifying, choosing an evaluation set of the proper size, let's take a look. The size of the evaluation set right here, 2 elements, and the degree here is 1. Take a look at this example. The size of the evaluation set is 3, and the degree here is 2. The fundamental theorem of algebra, the fundamental theorem of algebra states that polynomials of degree n minus 1 are faithfully represented by evaluation on n distinct points. That means that if we take an evaluation set of n elements, we may represent polynomials of degree at most n minus 1. We will take P and it will represent it as this list of values. It turns out that this operation phi, this is carried out by a matrix multiplication. We get the results, the list of values. We can think of them as a column, and we may obtain this list of values by multiplying the coefficients by a proper matrix. This is, in this case, an n times n matrix called the Vandermonde matrix, associated to the evaluation set x0 to x minus 1, associated to the evaluation set. And this is simply a matrix that contains the necessary powers of the evaluation points. The first row being the evaluation at x0 of the monomials. So the first power, the second power, the third power, and so on. The second row will be the same, but for the second evaluation point. It's this one. The last row will be simply the evaluation at the last evaluation point. Okay, so what happens here is that the process of going from coefficients to values is multiplying by V is simply matrix multiplication. And since each row has n elements, then there are going to be n multiplications for each row. Since we have n rows, this is order n squared. We need n squared operations to perform this transformation from coefficients to values. It turns out that we still haven't said anything about the structure of the evaluation set. It turns out that when we choose the evaluation points as roots of unity, and in particular when we choose roots of unity of order a power of 2, this complexity can be reduced drastically to order n times the logarithm of n when choosing the evaluation set as roots of unity of order a power of 2. Of the roots of unity of order a power of 2 will play a crucial role in easing the complexity of the problem of transforming coefficients into values. We're going to take a careful look at that in the following video by exploiting the properties of the roots of unity. Okay? For the time being, we need to think of all these parts coming together as parts of a much bigger problem. This will be helpful for us to think of how to reduce the complexity of a task when we are going to test for the degree of a polynomial. That is, we need to decide whether a list of values corresponds to a low degree polynomial. We're going to take maybe a similar strategy to this one. Maybe reducing its complexity, not by a logarithmic scale, but with a geometric scale. But the idea remains, okay? So we're gonna round this video here, and we're gonna follow the next one with an in-depth explanation of how these roots of unity actually help us reduce this complexity. Okay, see you in the next video.